The direct product. Anything that is not a direct product is entangled. So because we can write superpositions of states, obviously almost every single state in the Hilbert space is entangled. So entanglement is a generic property. It was known from day one in quantum mechanics. So why do we bother about it? In fact, not only that almost all states are entangled, but even if you start non-entangled and two particles interact, almost always they go out entangled. You really need to fine-tune things to make sure that you don't get entangled. Also, almost all Hamiltonians have their eigenstates entangled. And this was known from the beginning. For example, suppose I have
Recording has started.
Suppose I have a Hamiltonian between two particles, like sigma A or sigma B. The ground state for this of two spins would be 1 over root 2, say up, down, minus 1 over root 2, down, up, where this is up in the Z basis. But it could be up in any other basis. So this is an entangled state. And if you want to disentangle, since this is the ground state, you pay a big penalty in energy. So these things were known for a very, very long time. But what we have here, we mix together two things. When we look at what people looked at the beginning of quantum mechanics, we mix interaction with entanglement per se. And the great step forward was done by Einstein, Podolsky, and Rosen, who realized that interaction itself is interesting, that entanglement itself is interesting, even when we do not talk about interaction. So suppose we have two particles, like these two spins, that we separate. We send one in a galaxy, another one in a different galaxy. There is no longer an interaction between them. There would be no energy penalty if I move them in any way I want. However, they still have interesting properties. And that was probably the great step of Einstein, Podolsky, and Rosen. That was sort of PPR in 35. So what is the main thing about entanglement? Is that whenever you have two particles that are separated at a distance, and you perform measurements on them. You send two particles, you perform a measurement here, a measurement there. Then you repeat, then you repeat. You get correlations that are very strange. They are what we call non-local correlation or non-locality. And the idea is, well, if you ask a philosopher what non-locality is, you'll get all kinds of words. Elements of reality, local realism, and so on. But the best way to think is that if you were not using quantum particles, just using ordinary classical physics, if you were to try to produce these correlations, you would need to communicate faster than light from one part to another. Okay? In fact, so it is this characteristic that we are talking when we are talking about entanglement. This, in some sense, is a deepening of the most shocking thing about entanglement. For those of you that went yesterday to Lenny's talk, you realize, you may remember, that suppose I have a state like this entangled state here of two particles. I know everything about the entire system, which are the two particles, but I know nothing about each particle separately. Each particle is described by a density matrix, which is to say I really don't know. And in fact, nobody knows what its own state is. So this is the first shocking thing about entanglement. We can know everything about the whole system, but not know things about parts. And this allows us, and opens a window to get down to non-locality. Now, in fact, non-locality is a very simple thing, so perhaps I will take 2 or 3 minutes just to give you the simplest experiment, just so that we know what we are talking about. And here that is. Suppose I have a source here in the middle that sends 2 particles. Sends a particle to the right and a particle to the left. Now here, on the right, I have a measuring device. Here it has an opening in which the particle goes in, and the measuring device is just a black box, and it has 2 lights, a red and a green. And here the same thing. A measuring device and has 2 lights, a red and a green. On top of that, each measuring device has a switch that can be put into position, up or down. Up or down. I explicitly want to put things in this abstract way because it doesn't have anything to do with numbers or with a quantity that is measured or with anything else. So I keep them abstract. There is a measurement that can give only 2 possible outcomes, and there is a switch here which essentially says, if I put the switch up, I'm performing some measurement. If I'm putting the switch down, I'm performing another measurement. And here there are 2 experimentalists. Alice is on one side, Bob is on the other side, and what they can do is when the particle arrives, by prearrangement, they can be very far from each other on the more galaxies, they decide at random, just before the particles will arrive, what measurement to do, up or down. And much later, they will repeat this on many, many particles. And much later, they will come together and compare their results. And when they do that, they see some interesting thing. So here is a quantity that interests us. Suppose that I would consider success. It's like a game. I would prefer to phrase it like a game. This is a team game played by the particles. And the particles are successful in the following situation. If the 2 switches were put down, so if the down measurement was done, then they are successful if the answers are different, either red-green or green-red. For all other combination of measurements, down-up, up-down, up-up, the 2 particles are successful if they give the same answers. Alice and Bob choose at random which experiment to do. So each experiment will be done with probability 1/4. And the question is, what is the probability of success? So the best way to see this is imagine that you and your friend are the 2 particles. You are together here at the source, so you can talk to each other before the measurement. And then one of you goes on one side, the other of you goes to the other side. And you try to win this thing. You don't know what questions Alice and Bob will ask. So imagine that you go there, Alice says, I decided to put my switch up. You tell me what you want, green or red. And you have to say it. So, can you always win this game? Well, let's see how you would like to do. Since you want to keep this pattern of correlation, if you want to change your mind here at the last moment, then there is no way that your friend that came here will know. So the best would be if you make by prearrangement here when you leave some sort of strategy of answering the things. Now, because this is what you keep in mind, because you don't know what experiment will do, it would be good if you would decide already at the beginning what to do in all possible situations. So without any loss of generality, suppose I decide that if you see Alice putting her switch on up, you would say red. Okay, there is no loss of generality. Now, you want to be prepared that if Bob also puts his switch up, to win. Since already it is decided that this particle would say red, the other one must say red. Because they must, in order to win, they must say the same thing. So this particle decides, okay, this is their understanding. Red, red, they will always say red when they see the switch up. But you also want to win in the case Alice put the switch up and Bob the switch down, in which case, again, winning requires the same thing. Now, we already established that this particle, if it sees the switch up, and that's all it sees, it doesn't know about Bob, will say red. So here, I must have a red as well. And now, they will win also in this case. But they also want to win in this case, down, up. Up here is red, down must say red. And then they lose here. So this means that the probability of success is smaller or equal 3 out of 4. They can win in 3 out of 4 cases. They can do worse, but 3 out of 4 is the maximum they can do. Now, what happens is that if these are quantum particles in some entangled state, and up and down are various measurements they do. And suppose that they measure operators that have 2 eigenvalues, say a plus and a minus 1. In that case, P success, so this is classical. That's all you can do if you and your friend are going to play. But P success, quantum mechanically, can go up to 2 plus root 2 over 4. And 2 plus root 2 is larger than 3. So it means that somehow the particles do better than what you and your friend can do. But what you and your friend can do, yes please. There was a question?
Yes, from Matt. If we allow the particles not to be deterministic, can they do better classically?
Okay, the question is, if we allow the particle not to be deterministically, can we do better classically? The answer, this is a very good question. Fortunately, it's simple to answer, and the answer is no. So what would be the particle not acting deterministically? Would mean this particle is coming here. It was not yet completely decided what we'll do for up. So for up, there was some, not a fixed answer, but some procedure that was already established. And the procedure is, when I come there, I may throw a coin. I look at what question was asked, for example, up. Now I throw a coin, and based on the output of the coin, I decide what to do. Well, that coin could in fact have been already flipped here, because he will have to put some procedure for up and some other procedure for down. So there is no surprise. He doesn't need to know what Alice will do, because he has to establish these 2 procedures already from the beginning. So then he can even flip all these coins here, and hence we go back to the deterministic session. So nothing can be done classically more than in 3 out of 4 cases. Quantum mechanics allows something more. And this is dramatic, because the only way classically you could do is if you would have a mobile phone to call the other party, but say, you know, the mobile phones really need to work faster than light because they need to give the answer now, they cannot wait. So the mobile phone, you call and you say, look, I saw the measurement up, and I said green, you take care what you're going to say. And then they can win. And in fact, then they can win everything up to every single day. So even more than quantum mechanics. Now you would think that this type of correlation violates relativity in the sense that now you have signaling faster than light. But the point is that although the particles may signal faster than light one to another, the experimentalists cannot signal one to the other using the particles. What is the particles trick? Well, you see, winning, now we are no longer talking about this pre-arrangement, we are talking about signaling between the particles. And winning, for example, for up can be done either by red or by green. So if they sometimes say one thing, sometimes they say the other thing, we repeat this measurement many times, locally the probability for red and green is 50%, 50%. So locally you do not see that there is a problem. You'll only see the communication afterwards. So it is the fact that quantum mechanics is a fundamentally non-deterministic property that enables the existence of these type of correlations. Okay? In some sense, this is very important because when we think of quantum mechanics, we think, you know, either we try to have some axioms that say quantum mechanics is defined on a Hilbert space over complex numbers with Hermitian operators. But if we try to think of some natural things, then all it comes to mind are all kind of negative statements. Like quantum mechanics is non-deterministic. If I measure this, I disturb that, and so on. But now you realize that the fact that it's non-deterministic allows you to have no local correlations. So it's a bonus. And you can even turn things upside down. You say, I may have a theory that is non-deterministic, but it doesn't need to be non-local. However, if I want a theory that is non-local and at the same time does not violate relativity, it must be non-deterministic. Because if I move something here and something else wiggles there and I cannot signal, that thing must have been uncertain. So non-locality is a more basic feature of quantum mechanics. So non-locality comes up, and by the way, this happens only when the states are entangled. If the states are not entangled, I cannot beat the classical limit. So it is the non-locality that is the basic property of entangled states. And whenever we are looking for measures of entanglement, we are looking, in fact, for measures of non-locality. As a matter of fact, today, people talk about non-locality or entanglement as if they would be one and the same thing. But there was one of the basic theorems at the beginning of the 90s that showed that every entangled pure state, no matter how many particles, can lead to non-local correlations. That is not trivial, because before that it was only known that a very specific state, like the singlet state here, the singlet state that was here, leads to non-local correlation. But it was proven that every single non-local state does, as far as pure states are concerned. Okay, so that is the guiding thing when we think of determining measures of non-locality. So let me now, with this in mind, let me now go to bipartite entanglement. So let me consider a pure state psi of two parties, A and B.
Sandu,
Yes,
do you mind if I ask a question?
yes.
The theory that you just quoted, you said it applies to states with many particles. Does that mean there's a non-local test that involves only local measurements for every multi-particle pure state?
Yes, that's correct. That's
Okay.
correct. Okay. So let me now talk about measures of entanglement. Okay. So take a pure state A, and this is the standard thing that you will read in books or in articles. You write the density matrix, which is just psi, and then you define the reduced density matrix, rho A as being trace over B of rho AB, and similar rho B being trace over A of rho AB. And then a measure for entanglement, the entanglement of psi is just the von Neumann density, the von Neumann entropy of rho A, which is the same as the von Neumann entropy of B. That is what it is usually said. So, in particular, suppose that I have the state psi AB to be, say, alpha 0, 0 between Ellis and Bob plus 1 minus alpha squared 1, 1. Ellis and Bob. Then the entropy is simply minus alpha squared log alpha squared minus 1 minus alpha squared log 1 minus alpha squared. Okay, now, what do you feel, first of all, intuitively? If alpha would be 0, then this term would not exist, would be only here. If alpha would be 1, then only this would exist, not there. So then the state is not entangled. So you would imagine that I have a measure of entanglement, alpha 0 and 1, this is alpha, that should be 0 here and 0 there. And when alpha reaches 1 over root 2, both two terms are equal, then you would like something that would be maximal. So this is the sort of thing that you would like. And in fact, the von Neumann entropy has that shape. So you are happy. But if you think a bit more, you say, look, why should I take S and not some other function that is monotonic on S? Perhaps I would like to take S squared. Would still be something like this. Or perhaps I would like to do something else. Let me come back to this game here. Let me come back to this game here. Okay. The probability of success in quantum mechanics can go, of that game that I explained, can go up to 2 plus root 2 over 4. But in order to reach the absolute bound, you would need a fully entangled state. In general, probability, where shall I put here? Let me go back. Probability of success would be, let's say, 3 plus square root of 1 plus 4 alpha squared, 1 minus alpha squared, minus 1 over 4. And I wrote it in this way because this is the excess over the classical thing. So now you may think that perhaps this term here which shows by how much I violated the Bell inequality, is a measure of entanglement. So there are many competing measures of entanglement, and which of them should I use? Also, the other thing is when I want to go to bipartite entanglement, but in higher dimensional space. When I'm in two-dimensional, the most general state can be written in this form. It is in fact quite interesting that just a single parameter alpha can be used if I look at the correct basis. But suppose I have a state that is alpha 0, 0, plus beta 1, 1, plus gamma 2, 2, plus delta 3, 3, and so on. Now I have many parameters. How should I think of a state that is more entangled? For example, would I like a state in which all these three may be equal, although very small, and the variability for us with delta? Or shall I spread them in space such that they are equal? Which of those would be more entangled? There is not a single number to put. Perhaps I should think of many numbers that define the entanglement even by two-partite. Okay, so rather than go down to a formula, the idea was to see what we actually mean by entanglement. And we mean the basic element of entanglement was the fact that it is non-local. That's why I started. So, suppose that what I do, I have two particles, one here, one there, that are in some state psi. In order to produce entanglement, I had to make some interaction at the source. But by now, they are far apart. The question is, suppose that now I want to do some things on them, some sort of local actions. I can do some local measurement here and some local measurement here. So either I do unitary evolution, or I do measurement, and so on. And the same thing on the other side. Now, I can also do something else. I can also do classical communication. That is, I do a measurement here and I speak. Now, I want the entanglement to be something that is non-increasing under local things and classical communication. You and your friend, if you never met, but you speak at the telephone, you can create correlations between you two. Now, these are trivial correlations. These are classical correlations. I don't want to count them. So that's why I want something that, if I allow for classical communication, will not increase. So here we get already the basic element, and this is the thing that will guide us through this entire thing. I want entanglement should not increase by LOCC, local operations and classical communication. Local operation and classical communication should not increase. So we are looking for a measure that is not increasing under the things that we can do to the system. So in particular, if I go from a state psi of A to some other state, well, this is in general, to some other state phi, if I can go from here to there by LOCC, then the entanglement of psi must be larger, at most equal, with the entanglement of phi. That is the main thing. And this is the guiding principle for finding measures of entanglement. An example. Suppose I have the state alpha 0, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. I can easily go from this to 1 over root 2, 0, 0, minus 1 over root 2, 1, 1, just by changing the phase of 1. So it means that this state has larger or equal entanglement with that state. Okay. In this particular case, actually I can even go back. If I can go back, and this is the other thing that I will want to mark here, if I do that as well, then the two things must be equal. So the first element is non-increase, and the second most important thing is reversibility. Reversibility ensures equality over there. These are the things that we have to keep in mind. There are some transformations that are not reversible, but those in general use measurements and other things where entanglement is destroyed. Okay. Now,
LO allows measurements.
And local operation allows measurements. That is fundamental.
I have a question.
Yes.
So if I consider 3 parties,
Yes.
then I can measure 1 to increase the entanglement of 2 and 3.
That is absolutely true. You can measure 1. The question from the audience was like this. If I discuss about 3 parties, like in a GHZ, I can measure 1 and I increase the entanglement of the other 2. So that is not a good measure of entanglement. The entanglement of 2 when you are in a 3. So you see, already we have a bonus of understanding going from this principle. And I will talk exactly about that example a bit later. By the way, how am I doing with time? Okay.
We're not thinking we constrain anything.
Good. So, bipartite non-locality is easy because of the following thing. Suppose I have, okay. So the question is in general, that in general transformations that take a state psi in a state phi are not reversible. But for the very least, doing this thing, we start having an ordering between states, which is more entangled, or partial ordering between states, which is more entangled than the other. Fortunately, in the case of bipartite entanglement, I can have full ordering, not only partial ordering. And it goes like that. One thing that I can do is to do block processing. Suppose I have not a single state. In fact, with a single state, you never do anything. You have many entangled pairs. So I have n copies of some entangled state psi. What one can prove is that there exists a procedure that you perform local operations. Alice does a local operation on all her particles, not on each of them separately. And Bob does a local operation on his particles. And then they can create maximally entangled states here. Some number k of EPR pairs, where the EPR is, for example, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. And others will remain non-entangled.
As you said, the original state consists of a product in which each element of the product is partially entangled, maybe non-entangled,
Indeed.
maybe fully entangled.
Indeed.
Okay.
Indeed. So psi, for example, would be alpha 0, 0 plus beta 1, 1. Or in fact could be plus delta 2, 2, something. And I have many pairs of the same type. And then I can go from them to some number k of EPR pairs and some other particles, if suppose I have more pairs here that I'm ending up with, others remain in direct product.
This is something that's true for large N.
This is true. So what is true for large n is that it is reversible. So for when n goes to infinite, I have a reversible transformation. This particular transformation involves some measurements here and involves some communication. Now, you may think that measurements destroy the entanglement, which is true, but the amount of entanglement destroyed, this will be highly degenerate measurements, and they destroy a little bit. So technically, this is not fully reversible. If I start with n copy of psi, I go into singlets and I come back, I may lose something like square root of n. But in the limit of large n, the transformation is reversible. Because of that, I can start with psi, or I can start with phi, or I can start with whatever. I can go from psi to the standard EPRs, and from the EPRs, I can go to a state phi. So there is one single standard currency here. Everything can be converted down into singlets. So, and what is the ratio? Here is the interesting thing. So suppose that you want now to look, what is the ratio of k over n in the limit when n goes to infinite? This is S of rho A, where rho A is trace over B.
For the single copy.
Yes, for the single copy, for the single copy. So this is a quantity that you look at the single copy, but its meaning is that whenever you want to transform psi into singlets, this is the amount of singlets that you can get, okay, in the limit of large n. So that also tells that if I look for some that in the large limit, suppose the entanglement of n copies of psi must be the same as the entanglement of k copies of the singlet. And if I look for a linear measure of entanglement, I need n times the entanglement of psi to be equal with k times the entanglement of singlet. Hence, there exists a single measure of bipartite entanglement. E of psi, as long as it is linear, it is the ratio k over n es, and es are the units that we are looking for. And this is the measure of entanglement. It's not the entropy. The entropy turns out to be numerically equal to the thing. But the concept is, this is the standard currency into which I convert the things. By the way, here I said that these states could be living in a higher dimensional space. So in principle, the entropy could be larger than 1. So I could create even more singlets than states that I have here. For that, I need more particles here. I can take particles out of my pocket locally and put them there. Okay? So that is not a contradiction. Incidentally, this whole idea of doing block processing is an idea that is very common in information. So, in classical information. Suppose you want to transmit by fax a piece of, a page written. Now, if you look at that page is mostly white. So you want to send pixel by pixel. So essentially, if you would send pixel by pixel, you would have to say white, 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 black, black, white, 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 white. It's very boring. And in fact, it's very time consuming. It's much better to make a code to say million whites, black, white, 100,000 whites, black, black, white, and so on. So things can be compressed. But in order to compress, you need to process on a block. You look that there are 1 million whites, and then you say, if you were forced to send each of them separately, each pixel separately, there's nothing you can do. So this idea of block processing, first of all, is natural, because we always discuss about many pairs. And second, this is the standard thing that is done always in information. You can now say, look, but I don't want to do that, because suppose sometimes I have only a single pair, what can I do with it? Well, then you are more constrained. So things that are equivalent, when you allow to do everything, may become non-equivalent when you are imposing constraints on it. And then you have an entire zoology of things, even in the bipartite case. What to do when I can only process 3 pairs at the same time, and things like that. But basically, nature doesn't really care about that. If you really want to understand what is the nature of bipartite entanglement, all bipartite entanglement is the same, and it is singlet-wise. Okay.
Is it more or less true that if I have a very large system, a single very large system, and it's fairly generic, that the number of singlets that I can distill out of it is also equal to the entanglement entropy?
Okay, so the question that Lenny raised, I don't know if you heard, is that if I have a big, one single state, but of a large number of particles that are half of them here, half of them there, whether I can convert that into more or less this idea and say that it is like having identical particles. Well, that depends on how close your state is to such a decomposition. In general, the states that I know that you are looking at, they are roughly like this. But I may envisage states that are not at all like this, and in that case, you really have to consider that whole thing as a single copy. And only if you have many samples of those, you can do it.
I was thinking of pure states which are close to looking thermal locally.
Yes. Most probably the answer is yes in that situation. That is, but again, when it is bipartite, things can go wrong there. Because generally things are maximally entangled if one subsystem is much smaller than the other. If they are not like that, then one. But okay, that is an interesting thing, and I think that the background for this question is that if I really look single particle, then for all, single copy, then all transformation that I do are not governed by the entropy, because I have supplementary constraint. They are in fact governed, I will come later in the talk, by a large number of monotones, things that do not increase. Like in the case of something with all of these, there are plenty constraints. But for gravity, it turns out that it's only the entropy that is important. That must be due to the interesting structure of that single state, that single multiparticle state that you have. Okay. The other thing that I want to say here is that you see a sort of thermodynamic flavor. The entropy or the non-locality can only decrease by actions or remain the same. It is very much like the entropy only goes one direction. And because of this, one can see similarities between thermodynamics and entanglement. And in fact, this establishes the basic idea that we are envisaging at the moment in entanglement, namely entanglement as a resource, as a fungible resource. You are given some entanglement in some form. Suppose you don't want it in that form, you want it in another form, you can do it locally. You cannot increase, but you can convert. Very much like energy. You may have energy stored in a battery, which is some chemical thing, but you would like to have it like kinetic energy of a spinning wheel. You can do it without losses. You may degrade it. So it is very much the same thing. And this is the basic idea. Entanglement, and here I say bipartite, is as a resource. Good. So I made this very, very long detour in my talk of multipartite entanglement, and I didn't touch multipartite entanglement yet. So now there was a question?
Yeah, I just wanted to ask, you emphasized that you've got this nice formula, that the ratio of K to N was the entropy when you start with pure states. I'm just curious, if you have N copies of a state which is not pure, is there some corresponding simple formula for the number of PPR pairs you can distill?
Okay, so the question is, suppose that I don't have pure states, but I have density matrices of two particles. Is there anything like this? Well, the situation is far more complicated in that situation, because there is no transformation that is reversible. And when I say reversible, it's reversible up to square root of n. Therefore, all we know, and it took many, many, many years to prove this, whenever you want to distill singlets and then use the singlets to build back density matrices, you lose a given fraction of that. So there you can define now many different measures of entanglement for the density matrix. You may define an entanglement, so here for density matrices. Then you have entanglement of formation and entanglement question. Namely, how many singlets you need in order to form n copies of your states, and how many singlets can you get back. And it took many, many years to show that these two things are not the same. So by now we know that they are not the same. So that means that one may also want to find some other measures in between, and you open an entire zoology. The situation is complicated, that's what nature is. But the idea is that for all practical purposes, the fact that they are density matrix is that we do not have enough knowledge about them. So because we do not have enough knowledge, we cannot do the processing in a useful way. Now, things were not...
Can I ask another question to that?
Sorry, what was
I'm asking this question.
Yes, please.
Sorry, just a quick one. So where does the mutual information sit? Is it found above both of those two, entanglement of formation and entanglement of distillation?
It's somewhere in the middle. It's somewhere in the middle, actually. Yes. And there are some other quantities, and I will come back to them in the context of multipartite entanglement, because when I look at two parties between them, they are like in a density matrix. I will come directly to that. Okay. Why this was not clear that our lack of information may open a gap is because we are also not required to, to create things with complete information. Like we can start with density matrices and to do distillation and then create other density matrices back. It's a murkier thing. But the theorems that prove that these two things are not the same, they are very, very powerful and generic theorems. They are related to, there is an entire equivalence of theorems that talk about additivity of quantum channels and so on that can be mapped into the question of whether entanglement of formation and entanglement of distillations are additive or equivalent, and so on. Okay, but let me now go to multipartite entanglement. Pure states. I will just keep today pure states. So pure bipartite entanglement is just convertible to one single currency. Now, let's go to the meat of this talk. Multipartite. First, let me give you an example. A G8Z state. 1 over root 2, 0, 0, 0, plus 1 over root 2, 1, 1, 1. This is a GHZ state between three particles. If I have this state, can I decompose it into singlets? Into EPR. Okay. Well, we know some things. Suppose I have two singlets. I have a singlet here. I have a singlet, an EPR between Alice and Bob, and one between Bob and Claire. Another EPR. If I have these two states, I can definitely create one GZ. How do I do that? Bob locally creates, here's Bob, locally creates a GZ state. Keeps one for himself. Takes this one and using this singlet teleports it to Alice. Takes this one and using the other singlet teleports it to Claire. And like this, they end up with a GZ state. So, two singlets here, meaning an EPR, or let me call it singlet, it's easier, between AB plus an EPR between BC, they can go for sure into a GZ.
You had to use some classical information.
I always use classical communication.
So that's allowed.
That is allowed, because remember it was LOCC. We are allowing classical communication. So two singlets are stronger than a GZ. If I give you two singlets and you want the GZ, you can get it. Okay. From a GZ, if I can produce one single singlet here. How do I do that? That is exactly the thing that you mentioned. So for example, I have this ABC, and A will remain there. Alice would perform a measurement in some orthogonal basis here. So Alice will perform a measurement on the basis 0 plus 1, and will form what will remain on the other side will be a singlet. So the GZ is stronger than a single singlet between, say, BC. Or we can arrange a singlet between any other part. But this is obviously, so somehow I can convert between bipartite entanglement and tripartite entanglement. This is possible. But this particular transformation that I showed you here is not reversible. Okay? The question is, can we do something better? Can we do by block processing reversible things? And the answer is, in general, no. So let me give you first the proof in a simpler example. And this simple example is a four-partite GZ, GZ4, which is 1 over root 2, 0, 0, 0, 0, plus 1 over root 2, 1, 1, 1. Let me represent this state like this. I have the four parties here, Alice, Bob, Daniel. And the question, and I would have any copies of this. I want to make the block coding thing. And what would I like to do? I would like to convert it into singlets that are, and here there are other, they do not cross here. Some other singlet pairs like that, between A, B, C, and D. The question is, can we go reversibly from here to there? I have n copies of this, so I would like to put k, some k singlets between all these parties. Why would I like to do it symmetric? Well, this is symmetric, and if here I have some asymmetric thing, I can make permutations. It's the same thing. It's easy to see that if there exists a non-symmetric one with different singlets between the parties, I can also construct a symmetric. Okay, now we immediately see that this is not possible. Because in a reversible transformation, I can always view the system as being two halves. I will do a bipartition. And during a reversible transformation, the entropy of one side cannot go down. That is the measure of entanglement. So here, the entropy of A is just, well, the entropy in a single copy of A is 1, because this is just a sort of bipartite entanglement. It's like an EPR between a state of one particle here and a state of the other three. So this is n. That is because I have n copies. On the other hand, here, the entropy of A, S of A, would be 1, 2, 3, 3k, because there are so many singlets that happen. Now let me make a different partition here. Let me look at this bipartition, the entropy of A and B. If I look, this figure is a bit misleading. This is a JZ state. There is a connection there. But if I look here, say, is this versus that? Oh, AB, never mind. This versus that. So again, the entropy, let's say, of AB, just to follow that thing, is again n. Okay? But the entropy here of AB, well, if I look into AB, I have these singlets coming in, these singlets, those singlets, and those singlets. So it's 4k. So on one hand, you would like 3k to be equal to n. On the other hand, you would like 4k to be equal to n. This doesn't work. So this is the proof that multipartite entanglement, there must be irreversible types of entanglement or irreducible types of entanglement. There cannot be one number that catches everything.
Can you reduce it to a smaller number of GHZs?
Okay. The question was whether I can reduce it into a smaller number of GHZs. I will defer that thing for a couple of seconds, and I will come back to that question. Okay, what happens for the three-partite entanglement here of the three-partite GZ? Here, basically, I used only bipartite techniques to prove that I cannot have this thing. For three-partite GZ, for GZ3, suppose I look at two copies, just to look here, and I would look at three singlets. You see, the entanglement here, S of part A is 2, here, S of part A is 2. And it's the same thing because any other partition, this double partition of BC is the same as SA. So here, if I look at the entanglements, they seem to fit. However, one can prove in this particular case that the transformation is nevertheless not possible. Because apart from the local entropies, there is something else that is always non-increasing, and that is the relative entropy of entanglement of rho of, let's say, the part AB plus the entanglement of C. This thing always goes down or equal under reversible transformation, where this quantity that I would want to introduce for you is the following thing. ER of rho AB, the relative entropy of entanglement is done like this. First of all, consider the relative entropy between two density matrices, which is defined as trace of rho AB ln rho AB with a plus sign there, minus trace of rho AB ln sigma AB.
last question.
Was there a question?
Right. Suppose.
Okay. And now, the relative entropy of entanglement of AB is the meaning of sigma AB separable of rho AB sigma AB. That is, in the space of density matrices, here's my density matrix rho AB. Here I have a state of separable states, and this is sort of a distance towards that.
So separable means it's a product of.
Yes, they are non-entangled. They are not a product. In the case of density matrices, they are not entangled. What does it mean for a density matrix to be non-entangled? Is a mixture of direct products. Okay? It's not necessarily a product of two density matrices, but every single pure state in the mixture is direct product.
So it means it's a sum of density matrices, each of which represents.
It is a sum of density matrices, each of them that is a product. Okay. So this is, and we have now here the sum of two things. We have the entropy of AB, this relative entropy of entanglement of AB, plus S of C. And this is exactly what happened when from a GHZ state, I produced a singlet. In the case of a GHZ state, the entropy between A and B was 0, because they are like in an identity matrix. Well, then they are, well, it's a mixture of 0, 0, and 1, 1. Sorry, so they have no entropy. So this one is 0 as well. But there was a big entropy on the side C. Okay? And now I perform a measurement, I reduce completely the entropy of C, and I create some entanglement between A and B. So that is what is happening. But there is this quantity that depends on all three parties that should be conserved in reversible things. In irreversible things it goes down, but reversibly it must be conserved. Okay. And when you calculate this, then you, together with conserving the local entropies, then you find out that there is no possible reversible transformation between GHZ and singlets. So as we go to multipartite entanglement, there are irreducible types of entanglement that cannot be converted reversibly one to another. So this is the first lesson there, and then I will just say one more lesson, and that will bring us to an end for this. So the first lesson, there exist different irreducible types of multipartite entanglement. So you should not expect one single number. That is not the case. There are irreducible things. Question number 2. This is thing number 1. Thing number 2 there. Okay, there are a number of irreducible things. But suppose now I have some generic state psi between three particles. Psi generic, arbitrary.
Can I ask a question?
Yes.
That the first term in the sum that was decreasing
Was the relative,
what was it called?
relative entropy of entanglement.
So that's linear in the same sense, like if I take n copies.
I don't know what is the latest about it. But for the proof that we needed, it was linear because there it was 0 or non-zero. You'll have it 0 in the case of the GZ states and 1 in the case of singlets. Those two limits can be computed exactly. I don't know whether it was whether it's proven in general that that is a linear thing.
So the argument you gave extends also to block processing?
Yes, because in that particular case, my block processing either contained GHZ states on one side, and on those GHZ states, you know that the entanglement between two parties is 0, even in the n copies. And on the other side, there were singlets. And for the singlets, again, you can compute the relative entropy of entanglement for n parties.
So just to add a comment, there's definitely no proof that it's additive, or that it's additive in the sense that Matt was asking about.
Yes, but fortunately for that proof, I didn't need the full additivity of the thing. So just to clarify,
That's because you started with pure GHZ.
it's because I started with pure GHZ and then I can compute it exactly. So the question was whether the relative entropy of n copies of AB is the same as n times the relative entropy of AB. Whether this is a linear thing. And in general, well, if Patrick says that is not known, or was it proven that is not? Patrick?
So all I know is that it hasn't been proven that it's not.
Yes.
I don't know the counter.
But fortunately, in the situation that I was comparing here, for n copies of this, it's clear that the relative entropy of entanglement between A and B is strictly 0, no matter how many copies I get. And the relative entropy of k copies of singlet is, well, it's k times 1. So those are particular cases where I can compute the n copy thing.
Just to clarify, all this means is that if you traced out one of the pieces of the GHZ,
Yes.
the other two would be a separable density.
It's a separable density matrix, yes. And for the separable density matrix, it's clear that this is 0 no matter how many copies you have. Because those many copies you can imagine as a single copy of something separable, and the entanglement is 0. While for the singlets, you can compute immediately what is happening. Okay. Now, once we decided that there are irreversible, irreducible types of multipartite entanglement, we want to ask something more. Would it be, in the case of bipartite, I have some arbitrary state psi here that can be converted from n of these to k singlets, to k EPRs, singlets between AB, psi AB, and it can be done reversibly. Here, if I have n copies of some state psi, the question is it possible now to go to a set of all these? So for example, if they are, say, ABC, to some number G of GZ, plus some number SAB of singlets between AB, plus KAB, plus some number KBC of singlets between BC, plus some number KAC of singlets between AC.
Plus things which are...
Plus unentangled, yes. Plus unentangled. So the question is, I don't want to convert this into that because they are irreducible, but perhaps once I have a full set of irreducible things, generic states can be converted. And then we will say, look, tripartite entanglement is represented by four numbers. How much JZs, how much of this, how much of singlets like this, singlets like that, singlets like that. Sometimes we know that we can do it. Okay? There are some simple examples. So that is question number 2 is there, whether that is possible. So here is an example. For this, we know that we can decompose. And in fact, in this particular case, it's only GZs. There are no singlets. Here it's another. Where the states plus minus between B and C are essentially 0, 0, plus minus 1. Okay? This one is a great question. Nobody was able to prove that it's possible, or find a procedure to show that it's possible, or one that is impossible.
Possible means
That I have this state, and I want to decompose it into JZs and singlets.
Again, in the sense of block processing?
In the sense of block processing and of reversible. Yes, that is not known. So, there are a couple of possibilities.
So if you can do it with one copy?
Oh, with one copy, it's clear that you can produce sometimes a GZ or sometimes a singlet, but those are irreversible. But the question is this set here, which I will call M, these are M rings, the minimal reversible entanglement generating set? Don't ask. It was actually Charlie that came with this idea. Generally, he has better names. But, okay, M-Rex is what it is.
Charlie doesn't mean C.
Charlie doesn't mean C, it means Charlie Bennett. Yes, okay. Thank you for clarifying the talk. So what we don't know, perhaps this cannot be done in this particular set. Perhaps we need to add here something more. Perhaps there are more currencies to be put here, which may not be qubit states. They might be higher dimensional states. Okay. Which incidentally, we know that for 4-partite states, we may need to go to higher dimensional states and not qubits. But what is not known, so in general, is not known whether an M-ring is finite or not. It may be the case that there are an infinite number, but still much fewer than the total number of states in the Hilbert space.
What's known about W states?
W states, we don't know how we can convert.
Really?
Yes. So the only things that we know how to convert are these two things that I said before. This partial entangled GHZ, in fact, this is the only one that is.
So a thing as simple as a W state, which is a very simple state.
Yeah, we have no idea how in block processing, you know, let me make it clear. You heard sometimes that W and GHZ cannot be converted one into another. That is only a question about single copy. But in the case of multiple copy block processing, we don't know. We don't know even for a simple thing like a W state.
Maybe you should write what W is.
Yeah, the W state, here it's an interesting state. It is 1 over root 3, 0, 0, 1, plus 0, 1, 0, plus 1, 0, 0. This is the same thing as a particle being in 1 out of 3 locations. You have one particle here and vacuum in the other. It is exactly the same thing. And equals superposition. So this is known that in a single copy, you have zero probability to come from this to a GHZ, and from a GHZ you have zero probability to come to the double. So whenever I'm not allowed, this is probably the final message, unless people want to stay longer, they can stay as long as you want. So the message is that when I do block processing, many things simplify. When I'm not allowed to do block processing, means that things that used to be equivalent will become non-equivalent. And you now start having an entire zoology of possibilities. The other thing, so then really for quantum information, that is sometimes very, very useful, because in quantum information you say, look, I just send this state, what can you do with it? I'm not sending you an infinite number of states. I'm doing cryptography, I only want to do so and so. What is interesting, and this comes back to the question that Lenny asked, it appears that in these things, in Ryu Takanayagi and so on, although you think of a single copy, it's just only this single field theory here, not n copies of it. Nevertheless, it's still the entropy. So that is probably because the structure of that thing, although you have a single copy, but that single copy is like, of a field theory, is like multiple copy of constituents. That is something that actually has to be made very, very clear. Intuitively, I believe that is the case. But it would be very nice to see it exactly.
Sorry, you mean the fact that entropy is equal to area?
No, the fact that the non-locality is given by the entropy. You see, that entropy has operational, is a number. You calculate it. For every state, you calculate the number. The question is, does it have an operational meaning? And the operational meaning that I described was that when I have n copies, many copies, I can get fewer copies of singlet in this ratio that is given by the entropy, by the von Neumann entropy of the reduced density matrix. So I can calculate numbers for whatever I want, but the question is, do they have physical significance? So there it had. So now, the question is whether this single copy of the thing has significance, and probably it's because it's like a composite of many.
Related to, go ahead. Oh, sorry. So related to Lenny's earlier question, so when I look at a state that has a lot of degrees of freedom, and I want to approximate that, well, you said that sometimes it approximately looks like many copies of a simple system, so this applies. So is there a quantitative measure how like some states are better approximated in this way? In other words, there are some states where entropy makes sense for a single copy. Like I would guess, like if the density matrix has an eigenvalue which strongly peaks somewhere, then it works better. Is this a right?
Look, all these things are basically related to the. So I don't know if did you hear the question right?
You repeat it, please.
So the question that was asked here was, suppose I have a single copy of a state where the two parties are made out of many constituents, but I have a single copy, and this state is not necessarily decomposable into individual singlets between. So let me put it on the board. Suppose I have a system that is composed of a number of particles here and a number of particles there. And I have a single copy psi, which is A1, A2, AN, B1, B2, BN. So I can look at this. This is a psi, a bipartite thing, psi of A and B. Okay. So the question is, sometimes this thing can be seen as being composed of all kind of individual things entangled one with another. And in that case, this is very much equivalent with having psi to the power, I don't know, psi times psi times psi times psi, just AI, BI, and so on. So in that case, this is like one of my blocks. And although I can think of single copy, this one to be brought into some other copy, phi AB, it is essentially a block copy of many things. So only when it is like a block of many things is the entropy that has an operational meaning. Otherwise, if it is not equivalent with this, the entropy does not have an operational meaning. So the question was, suppose the state is not exactly like this, but it's an approximation.
You could scramble one side.
Oh, I could scramble, but then that would not matter. That will be just a reformulation of these
Right,
things.
but it's much more complicated.
Oh, it's much more complicated to do. So then my conversion will be first unscramble, then do the protocol, then scramble back.
Yeah.
If you want to scramble back.
Yeah.
But in general, it will not look like a product, but will be plus lambda something else. So this would be, you know, some, and it depends on the measure of what is the something else that is here, whether then I can see them as a single copy or not. But in general, the way to do that probably is to diagonalize the density matrix, see what is its typical subspace, and so on. I don't think that anyone looked carefully into this, but it's a very interesting
So
question.
you could ask the question, for example, supposing you take the whole system to begin with,
Yes.
you put it in some hard random state,
Yes.
and then you split it into two parts.
Okay. Will that be like a multiple copy?
Will that be like?
So the question that Lenny asked was like this: suppose I have a system made out of two n particles. I pick some random state according to the Haar measure, and then separate n here and n there. The question is, does it look very much sort of like many copies?
Yeah.
And if it looks like that, then the block processing thing, which leads to entanglement being the entropy of the local density matrix, applies. Most probably one can answer easily that thing. So I leave it as an exercise for student and learner. Yeah, I think that can be done.
Students could go like it.
Yes. Well, I can also talk what happens if you go down to single copy processing, which is exactly the opposite end of this story. But I'm aware that I went well over the time, so if there is any desire, I can continue on talking.
Before you do, let me just ask a question.
Yes.
So you said a minute ago that you thought you might conjecture that the Ryuta-Hinagi formula does have an operational meaning.
Well,
even though it's only one copy. Is there any evidence for that?
Well, you do apply the Ryuta-Hinagi using the fact that the entanglement is measured by the local entropy. So this is an indication that somehow what is behind it is the fact that that single copy effectively splits into many parallel copies of the things. Otherwise, I would be very surprised why that number that you compute, which is the local entropy, has any meaning.
Well, but I'm not sure it has meaning in this sense. I mean, the Ryuta-Hinagi seems to give the von Neumann entropy even when you apply it to states that are not pure.
Oh, well, it gives you the von Neumann entropy. The question is, what does that von Neumann entropy actually mean? Because
right.
I can get two parties that are absolutely non-entangled, but with enormous von Neumann entropy. And then that phenomenon entropy means really nothing for entanglement. For example, I can have two systems that are in identity density.
Right. I think what Don is saying is there's no particular evidence that it does mean anything.
No, but it does mean the area. So area is something you can measure in the system.
But does it mean the area even
In that
if you
sense.
put everything at infinite temperature and you have zero entanglement everywhere? And the entire CFT is not in a pure state, but it just, well, in that case, I don't know what it means. The good thing is that I'm not an expert in that area, so I can always have. So I don't know. Is it the case that it talks about the geometry whenever the things are not pure?
So, for example, you can have your whole system at some finite temperature, even sufficiently high temperature, so that the entropy of some region is actually dominated by thermal entropy, with only a small contribution from entanglement. And we believe that you're talking about isotopes is the right answer in that case.
Okay, but that's more like
So something that can be said. In the case, maybe we should turn off the room mic. In the case that the global state is pure, there's sufficient concentration in the entanglement spectrum that the interpretation in terms of distilling singlets between the system that you're entropy you're evaluating and the complementary system that purifies it is the correct interpretation. So you don't need the many copies. This is a corollary of something that appeared in a paper with Brian Martek and Ima, the information theoretic interpretation of the length of the curve. And I think that generalizes beyond the case of a 1 plus 1 dimensional boundary.
So what is the specific property that you need there?
The
Because
specific property
generical is not true, but
yeah. So what can be said is that if you the technical term, right, is that you evaluate the smooth one-shot max and one-shot min entropies. So you really look at how the largest eigenvalue of the density operator behaves after you truncate it a little bit, and that then determines the number of singlets that you can pull out of it.
okay, I see. Yeah, I understand.
And that can be controlled very explicitly in the case of a 1 plus 1 dimensional boundary. And then Brian has calculations that argue that this is also true in higher dimensions.
Okay, so probably that is equivalent to the question that was asked here. For which state that is a state of a single copy but of multiple things, effectively it works like many copies. So probably this is encoded in that property of the smooth.
That's right.
Patrick, is that a feature of the large N limit, N meaning the size of the gauge group, or is that?
Not necessarily. In that the statement that ends up being true is that if you take a large enough boundary region, the amount that you lose becomes sublinear in the entropy. Right. So basically, when you try to distill singlets, you would say the number I'd like to distill is the entropy, and what you find is it's the entropy plus or minus a correction term, which is sublinear in the entropy. So as long as the entropy is really big, then this will be true. So you can make the entropy really big by, say, making a large central charge, or by just taking a large region.
Good. Okay. Good. Okay.
Well,
do you want me to comment a little bit more about single copy, or we just bring it to an end?
Is that where you have different, you want to say more distinct families in the three-partite case, like the W state was mentioned? Because I remember.
Yes, that is one of the aspects.
So your point is that it's actually harder to make these distinct families in the asymptotic case, where you have the block processing and irreversibility?
Well,
or three-partite system?
no, the point is exactly the opposite, is that if I'm allowed to work block coding, I can do transformations that if I'm forced to do single copy, I cannot do. That is the thing.
But you can't then easily form these families with the tripartite system, whereas with the single copy, you could say,
Well, with
these
a
states are incontrovertible.
with a single copy, almost everything cannot be converted into anything else. And let me give you at least that argument. Okay. So, because that thing with W's and J, Z, V, that is just one particular aspect of it. Suppose that I'm now talking about single copy. So I have some state psi. Let me first just show you something of bipartite. This psi is alpha 0, 0, 0 plus alpha 0, 1, 0, 1 plus alpha 1, 0, 1, 0 plus alpha 1, 1, 1. So how many parameters we have here? Well, we have 4 complex, so it's 4 times 2 parameters. Out of this, I have to, so the number of parameters that parameterizes the state is 4 complex thing, so 4 times 2, 8 reals, minus 1, that is normalization, minus 1, that is a global phase. So overall, I have 6 parameters. Now, how many of these 6 parameters tell me anything about entanglement? Well, the claim is that out of these 6 parameters, I have 1 non-local. Why is that? Well, you imagine I have a particle here and a particle there. I can perform some unitary thing here, a unitary on A, some unitary on B. I can rotate bases. When I rotate bases, of course, I will change these numbers. Okay? So some of them can be changed when I do these local things. And I want to see what is invariant. Now, for a bipartite thing, you know, but I will put them in a general context, that I can write the same thing in the Schmidt decomposition. Schmidt basis. And that would be just alpha, say, I will put here like spins. Say alpha up, plus beta, the square root of 1 minus alpha squared, down. So the same state psi that was in general alpha up, plus alpha up, down, alpha down, up, plus alpha down. In some other bases, in some other prime bases, can be written with a single number. Now you see what is happening. If you make a local rotation, you just tilt this spin or tilt that spin. But that cannot affect the alpha. Okay? So there is one coefficient out of the 8 that are out of the 6 that are somehow encoded here that cannot be affected by local things. So it means that that is the non-local coefficient. And that characterizes the entanglement of this thing. In group theoretical things, you would say, look, I'm talking about, here I had SU 2 to the 2, and I'm not interested cross SU2. So I'm interested only in orbits. The full space, you imagine that you have these 2 spins that you can do whatever rotation, and that discusses about the full space. but you are interested only modulo individual rotations. And then you have different orbits, different sets. By making rotations, I can move inside each of these sets. And the number alpha just indicates on which set I am. And I have a lower one here with alpha equals 0, and here it's alpha equal 1 over root 2. And you can do a foliation of the Hilbert space into these things. And the local things just tell you where you are on the orbit. Now, this view that out of 6, only 1 is non-local is extraordinarily misleading. Why is that? Because in the bipartite qubit case, there is only 1 non-local parameter out of 6 parameters overall. Now, this is highly, highly misleading. It's correct, but it is misleading. That's why I took it. Let's look of a state psi of n particles, A up to n. So here I have, it's from A alpha 0, 0, 0, 0 up to alpha 1, 1, 1, 1, 1, 1. So I have 2 to the n complex amplitudes. Times 2 again. So it's 2 to the n times 2 minus 1 minus 1. This is norm and this is phase. But it is an exponential number of parameters. Now, if you apply local unitaries, u on A, cross u on B, cross u on C, so on, the number of parameters that describe, each of them has some finite number of things that you describe in the unitary. Say, if they are qubits, then you have 3. So it's 3 to the n, 3n parameters. So you have 2 to the n, and you only can control a number that is linear in n. So the vast majority of the parameters here are actually non-local. But that is an enormous proliferation. Even if you are allowed to do measurements, so you are not unitary, but you have here, I don't know, some projectors, then you will have 4 or 5, whatever.
But the system is divided into 2 parts, so bipartite, and I'm allowed only to do unitaries on even.
I guess Sandu is talking about multipartite.
Here it's about the multipartite.
I understand.
Yes. So in the multipartite, almost everything is encoded in non-local thing. By the way, this is how you see the fact that we can do quantum error correction in quantum computation. Because generally, the noise is local. And the basic idea is that we encode things into highly non-local states. That is the whole message behind these error-correcting codes and everything. Is the fact that locally I can only affect so many of these parameters. But there is a large number of parameters that cannot be affected by local things. So the entire trick there is to be clever and to encode your information into those. But you know, this is going beyond this particular code and that particular code and so on. This is why we get it.
So,
yes.
I have a related question. So this is, I mean, if I only consider local unitaries, it's mathematically clear what are the entanglement properties,
yes,
which are just invariant under the local unitaries.
Indeed.
But the LOCC is different from local unitary. So reversible LACC, does that form a different group than which is supposed to be bigger than the...
Okay, so the question was that when I consider local unitaries,
and the classical communication.
Yes, without classical communication, it's pretty clear what I mean by reversible transformation. All it means is to be on the same orbit. Even then, as a matter of fact, it's difficult to calculate the invariance. And you may have, because you would like to know whether two states, if I give you two states, are they on the same orbit or not?
Yeah.
Generally, that is complicated.
There is a series of papers by Wallach.
There are many papers, yes, on this thing. Noah Linden and I have some. By the way, talking about papers, this, let me see. I made a little note. So, all that my talk today is based on papers number 24, 33, 51, and what is this? 35 on my website, which is not my university website, but is Sandu Popescu.com. So no dot between them. So you go there, and this is in fact the order that I was talking about. You can download those papers from my list of publications. Well, when we go to block coding and to all processing, but first of all to say, even this thing, you would imagine that mathematicians solve this thing where you have you take these groups and you have like direct products, and you want to look at this sort of SU 2 to the n quotient SU2, SU2, and so on. And you think that you will go and read the invariance from a textbook. To my surprise, that is not the case. Or well, let me put it like this. I asked many mathematicians when I was interested in this. None of them knew it. Perhaps it is known. When you go to this block processing, it becomes very complicated, and it becomes really and classical communication becomes a really complicated piece of group theory. Even to formulate it group theoretically, it's not clear, because it's not clear how we put the classical communication. Plus, you are not always successful. That is, that procedure may fail in a sublinear number of cases. So they are sort of fuzzy equivalences that from a strictly mathematical point of view. Okay. Did I succeed to kill somebody with too much information? Okay. So mathematically, I haven't yet seen anybody being able to even formulate it precisely.
I mean, by the definition, it is a group, but it's just we don't know what group it is.
But also the fact that the equivalence is not strict. You don't go here and come back with certainty. You may come back with some probability of failure. So whether that can be encapsulated by a group, I don't know. I think this is look, it's such a natural problem for physics. It must be a natural problem in mathematics, but I don't know. I'm definitely, my mathematical level is not there, so that's clear. And by the way, the last thing, talking about orbits, some of these orbits are special because they have more symmetries, like the direct product states and the singlets. They have more symmetries than the other groups. They have bigger stabilizer groups. So probably when you go to try to find various irreducible types of multipartite entanglement, these sort of orbits that have special properties are important. But that's enough for today. Thank you very much.
Thank you.